Hello, my name is Erica Carlson. I'm a theoretical physicist here at the Purdue Quantum Science and Engineering Institute, and we're delighted to have visiting with us this week Claudio Mazzoli. Claudio is a scientist at Brookhaven National Laboratory, and Claudio, you run a rather large piece of equipment there, right? You run a beamline. Can you tell us a little bit about what that means?
Yes, a beamline is a piece of essentially a lab attached to a synchrotron that produces X-rays for science. And we extract those X-rays, we treat them, and we use them for studying materials at high level, let's say, deep into the electronic behavior.
Very nice. Okay, so the piece you run is attached to a synchrotron, and how big is that synchrotron?
Synchrotron is a big beast. It's a very big machine run by many people, trying to make the electrons to run in a circle that is roughly half a mile of length in our case. It can be much smaller or much bigger, but typical scales are yes, half a mile, let's say. Yeah.
Okay, all right, so a pretty large piece of equipment, and then the part that you're in charge of is one of the beam lines. So tell us what that is like. You know, if we were to visit your beamline, are we underground? Are we above ground? Do we have to wear funny suits like they do in fabs?
No,
what's it like?
We are not in space, so
okay.
no funny
not
suits.
Yet.
Not yet.
Right.
But yes, essentially you have a pipe, evacuated pipe. We need a very high vacuum to extract X-rays from the machine and treat them with a piece of optical equipment, and then make them impinging on the sample that we want to study. Then the X-rays are distributed around the sample, let's say, and the detector flies all over the place, always inside vacuum, to collect what is re-emitted by the sample, and this will tell us how the electron behave into the sample.
I see. Okay, all right. So basically, what you'd be studying there is another scientist perhaps would come to you with a material that they're interested in learning about, and one of the ways. There are many ways we learn about materials, okay? But one of the ways that we can learn about materials is by shooting particles into it and watching how those particles bounce through the material or bounce off. And so that's basically your expertise, is that you have these X-rays that you then shoot into the sample, and you're mostly, I think, watching how they come out the other side, right? Or are you also doing reflection mode?
Yes, essentially we do everything. We
okay.
do transmission, so going through the material. Sorry, I should do it like that, going through the material. And then what bounces back, as she was saying, or what is reflected at small or high angles. So everything brings out a different information, and the challenge actually is to try to understand which part of the information that is produced by the sample is relevant for our study. And so it's a kind of, let's say, finding the small tiny little piece of information out of many that are produced. There are parts that just tell us how the electrons are on average distributed, how they move, if they bring magnetic information or not, and so on and so forth. So we need to dig a little bit into the information to deepen our understanding to those details, and sometimes it's very tough.
Okay, so you get a lot of data out of this, right? Are you connected with big data ideas in science right now?
Absolutely. Part of the effort at BNL is indeed to try to rationalize all this big data, try to use artificial intelligence, try to use good way of storing data, which is per se a big trouble. And just to give you a number, we are not one of the beamlines that produces most of the data, and this is related with the size of the detector we have. The detector is very specific, very good actually. It's a collaboration with Berkeley, and it's very fast for being soft X-rays related. Our challenge is, as I said before, maybe a little bit quickly, so I reiterate, is the fact that our detector sits completely in vacuum, so it cannot be obviously massive. Otherwise, we would need a massive environment under vacuum, which is technically not feasible. So our detector is more or less this size, and it has 1,000 by 1,000 pixels. So this limits somehow a little bit the capability of producing data that we have. But still, if it were working in continuous mode, we would produce tens of terabytes of data per day. Obviously, hard X-rays that do not have the constraint on vacuum can profit of much larger detector, and so actually they end up being the beamlines that produce the most of the data out of the synchrotron, and it can be a couple of orders of magnitude bigger, probably, per day.
Okay, all right, so big machines and lots of data.
Yes.
And so lots of stuff to think about, which is, of course, what scientists love, right? We love to have lots of interesting physics to think about. One of the things that I think is very exciting about our subfield of quantum science, which is quantum materials. We work on quantum materials. One of the things that I think is so exciting about quantum materials right now is that we have the opportunity not just to discover what's already out there, but people are designing new materials. And so we're designing this frontier as we explore it.
Yes.
And so I'm curious, what, in what you're working on, is there any, you're working on a lot of exciting stuff, but is there maybe one thing in particular you'd like to highlight for us that you think is that you're particularly excited about right now in your own research?
I'd say I'm really lucky because many interesting scientific problems pass through the Beamline. Either we bring them or users bring new problems. And let's say that the one that catches most of my attention and interest at the moment is certainly superconductivity, high temperature superconductivity. I'm trying with many others, obviously. We are trying to get a better description and to understand better which is the link with other, let's say, all the electronic degrees of freedom, so structural, spin, so magnetism, conformation in space, and so on and so forth. And we are trying to get a better description because, believe it or not, it's eluding our understanding since quite a while by now.
Ouch. Okay, so I'm a theorist, and I have worked on theories of high-temperature superconductivity. And like many theorists who work on high-temperature superconductivity, I know how they work, but we don't agree. Several people have a lot of different ideas,
yes.
Which is why we say there's no consensus in the field yet. And as a theorist, we really rely on scientists like Claudio to go into these materials, measure them relentlessly, and continuously push forward the boundaries of human knowledge there so we can test the different theories, right? There are different ideas about how they work, but we don't know what's actually happening in a particular material until we go in and look at it. And so this is why there have to be discussions between theorists and experimentalists, because that's how we find out what's actually going on inside of materials. So
we are the two halves of the same apple, right?
Right.
Probably Newton's apple.
Oh, sounds good. Sounds good to me. Sounds good. Yeah. So I'm also curious. What made you want to go into science in the first place? So as you were sort of choosing a career, were you trying to choose between one career and another, and what ultimately drew you into the sciences?
Let's say that since a kid I was always interested in either going to the moon or understanding how things work, and I found over time that the most exciting part was actually related with understanding what the electrons do in material. So this is what has driven me to this point, essentially. And as I said, I'm very lucky because I'm in a fantastic position overall to deepen my understanding and helping the community.
Very nice. Thanks. Okay, so we're running out of time, so we'll just go ahead and end this. But I look forward to many more great conversations with you during your visit here. And thanks for visiting us at the Purdue Quantum Science and Engineering Institute.